Hi, welcome to our AI project on predicting cardiovascular disease. Over the past couple of years, cardiovascular disease has contributed to roughly 32.9% of the world's annual death count, or about 18 million deaths. In Singapore, since 2019, cardiovascular disease has been on the rise, causing an increasing number of deaths year on year. Through extensive studies, scientists and researchers have been able to evaluate that cardiovascular disease is a result of many different factors that compound together. As such, with this AI model, we're aiming to predict if a person might have a cardiac episode based off some key indicators about a person's current health status. We believe that a successful model can be used preemptively in applications such as Health Hub, by tying it together with present day health tracking apps and devices to warn individuals. Additionally, we also believe that this model can be used for medical triaging within healthcare institutions to identify those who are at more risk than others. Our presentation will include how we carried out data processing, a choice analysis of our models, and a conclusion to tie up our results together. For data processing, we use a dataset found on Kaggle containing 70,000 values of patient data collected when they were admitted to the hospital, including basic values such as height and weight, as well as more technical values such as blood pressure, cholesterol levels, and whether an individual has had a cardiac event occur before. First, we remove duplicates and then transform the data by changing the age variable to represent conventional age instead of age in terms of days. We also split the gender column into male and female for better analysis. After printing the correlation matrix, we identified that there was no strong correlation that the variables had to whether an individual experienced a cardiac event, but relatively, the values to take note were age, weight, and cholesterol, which had the highest relative correlation to the cardiac variable. From there, we proceeded on to data cleaning by cleaning data that was numerical in nature, such as height and weight. By viewing them together, we were able to find the mean and standard deviation and give a slight buffer for this value range. This process removed 359 total values. After that, we looked at cleaning the dataset based off blood pressure. Using a blood pressure chart as reference, we found an optimal range and represented that in the form of a box plot for the two types of blood pressures. Removing values in this range resulted in the removal of 1,479 values. From here, we could conduct some basic exploratory data analysis to determine some statistics, such as identifying that cardiovascular disease occurred in approximately 50% of the dataset. This will help with eliminating classification bias during the machine learning stage. Furthermore, we were able to identify mean, standard deviation, and other factors for the numerical analysis, which will help in our analysis later. Finally, printing out the last correlation matrix, we were able to see some major changes such as systolic and diastolic blood pressures correlation increasing. We were also able to validate some of our basic assumptions to a certain degree, as the correlation values were still considered to be in the lower range. Now, moving on to the models of our choice.
And now I'll be looking at models to help predict cardiovascular disease from our dataset.
I'll be doing logistic regression, classification tree, and k-nearest neighbors.
And I'll be using random forest classification and neural nets.
Now we'll be looking at random forest classification. Random forest is an ensemble learning method that combines multiple decision trees. Each tree is trained on a random subset of the training data. The final output is obtained by aggregating the outputs of all individual trees using a majority vote. This model is advantageous due to its robustness, its ability to handle non-linear relationships, and its overfitting resistance. Coming to the input and output of the random forest classifier, the input of this model, like future models, is features underscore train, which is a set of extracted features representing cardiovascular risk factors. The output of this model is binary classification, predicting the presence of cardiovascular disease, 1 being present and 0 being not present. The provided code sets up a random forest model with a randomized search for hyperparameter optimization. The random forest classifier is instantiated and optimized using random search CV to find the best hyperparameters through clause validation. In terms of the hyperparameter choices, the three most important are n underscore estimators, which is the number of decision trees in the random forest ensemble, max underscore depth, which is the maximum depth of decision tree, min underscore samples underscore split, which is the minimum number of samples required to split an internal node in the decision tree. Some other ones are min underscore samples underscore leaf, max underscore features, and bootstrap. By employing this randomized search CV, an efficient optimization technique looks for the best hyperparameters. This random search will test 20 different combinations using a 5-fold cross-validation method that tests the model's performance using different hyperparameters to come up with the best one. In terms of the evaluation metrics, we have accuracy, precision, recall, and F1 score. And the accuracy achieved by this method is 73%. Coming to neural networks, the reason for choosing neural networks is simple. It has complex pattern recognition and has multi-layer representation as well as adaptive learning, which will help us find if someone has cardiovascular disease or not. In terms of what a neural network is, a neural network is a number of artificial neurons represented in a layer and a number of hidden layers represented in a network. In terms of the input and output, it is similar to the random forest classification, except the dataset is first processed using pre-processed by dropping missing values and standardizing features using standard scalar and encoding the target variable. In terms, The provided code constructs a neural network model using the Keras library with a sequential model consisting of dense layers, which are fully connected layers. It follows the standard steps of building, compiling, and training a neural network model. In terms of the model architecture, the architecture has 4 layers, including 2 hidden layers and an output layer. The input layer has 64 neurons, and the hidden layers has 32 and 16 neurons, respectively. The output layer consists of 1 neuron. In terms of the hyperparameter choices, the 3 most important ones are the number of layers and neurons. The neural network consists of 4 layers, as I said before. These values are chosen based on the complexity of the problem and balance between the model capacity and the computational cost. In terms of the activation functions, the 2 input and the hidden layers use ReLU, which is a rectified linear neural activation function, which helps in alleviating the vanishing gradient problem during training. In terms of the output layer, we use a sigma activation function since it better represents the probabilities and maps the output between 0 and 1. The loss function used is binary underscore cross entropy, which is suitable for binary classification tasks. The optimizer uses add-in, and the batch size is 16 and the number of weeks also 15. This is taken to maximize the output while minimizing the computational cost. In terms of the evaluation metrics, the evaluation accuracy achieved by a model is 72.76%. And yeah, on the right, you can see the graph which measures the accuracy across the different epochs.
The third model is binary logistic regression, which is a supervised machine learning model that is suitable for our problem because we have a categorical dependent variable of whether a person has cardiovascular disease or not. The model makes use of a sigmoid function and is very efficient to make predictions. We evaluated this model using a confusion matrix, and the highest accuracy achieved is 71.9%. The fourth model, which we are comparing with, is the classification tree. Similar to logistic regression, it is supervised, and we use 2 layers of classification. This model is good for helping find data that can be omitted to further optimize predictions based on the Gini coefficient. However, this model may not be optimal as it is based on a greedy strategy. We evaluated this model using the confusion matrix, and the highest accuracy we achieved is 71.3%. Our next model is the k-nearest neighbor classification. We evaluated this model using the confusion matrix, and the highest accuracy we achieved is 73.2%. So based on the models thus far, the model with the highest accuracy is the k-nearest neighbor, or KNN for short. Therefore, our chosen model is the KNN model. KNN is a supervised machine learning model based on the assumption that things similar to one another will be located near one another. The model will classify a data point based on the most common class of its neighbors, and the number of neighbors is based on the k value used. So if you look at this diagram, to classify a data point, the model calculates the distance from the data point to its neighbors. And because k is set to 3 and 2 neighbors are of class B while only 1 neighbor is of class A, the model predicts the data point to be of class B. For our model, we ran the model using different k values from 1 to 199, and the k value that gave us the highest accuracy is 103, as shown in the KNN accuracy graph that we have plotted. For the inputs, we take the clean data and split into 70% trained data and 30% test data. We then use the trained data to train the model, and then use the model on the test data. The model outputs a list of zeros and ones, with 0 denoting no cardiovascular disease and 1 denoting otherwise. We chose KNN for 2 advantages. Firstly, KNN does not assume a linear relationship between data points, which is more realistic in making predictions, considering that the variables involved may have a complex relationship with one another. For example, smoking is not linearly related to cardiovascular disease. Secondly, KNN is also able to provide high accuracy when the optimal k value is used. A high k leads to high variance and low bias, which denotes overfitting, and a low k leads to high bias and low variance, which denotes underfitting.
Now I'll be talking about the conclusion of our project. I'll be summarizing the findings as well as evaluating the limitations of our model.
In conclusion, we evaluated 5 models: logistic regression, KNN, classification tree, neural network, and random forests. We chose the KNN model as it has the highest accuracy, although it has its limitations. Firstly, it can be sensitive to irrelevant features in the dataset. This can affect its accuracy, and to mitigate this, the dataset should be clean and each feature should be checked to see if it's relevant before using. Irrelevant features can be removed to reduce the dimensionality that the model has to deal with. Secondly, because the model has to store its training data, it can be computationally expensive, and this increases the time taken to find the optimal k value. To mitigate this, there could be a threshold to cut off the search for k value. For example, if k equal 103 gave the highest accuracy, and from k104 to k109, the accuracy is not more than the highest, I can stop the search for the optimal k value. And with this, I end our presentation. Thank you.
I'm having a heart attack.
Oh my god, he's having a heart attack!
No, he's dead. But he could have been saved if he used our model.